Hello again. I hope you've had a chance by now to learn a little bit about energy levels and a bit about how we understand the energy levels and the shapes of the regions in which electrons are found in the atom. We've talked about different shapes like sphere-shaped shapes, figure eight or hourglass shapes, cloverleaf shapes, for all different sorts of electrons. We've talked about the S, P, D, and F, electron energy sublevels or blocks of our periodic table. And we've kind of organized our sort of blank template periodic table here in a way that's a little different than we'd usually see it on a poster or in something in your notebook, where we'd have all the elements filled in, where these boxes of our periodic table represent electrons. And so just to kind of quick recap what we saw in that last video, hopefully you had a chance to watch it. The idea that these different blocks of our periodic table can be numbered and sort of lettered with a set of codes that represent the different sort of ways that electrons behave if they fall into different parts of an atom. And depending on how many electrons an atom has, it'll have different electrons in different shape regions at different distances from the nucleus that we call energy levels. And so this sort of summary, I guess, that we had at the end of the last video, where we've broken down the periodic table into four main blocks, the S, P, D, and F blocks, and that those blocks are further divided into sort of numbered parts that match up with the average distances from the nucleus that we recognize as the 7 energy levels of a large atom. Now again, most atoms don't have 7 energy levels. Only the last few elements of our periodic table would have 7 energy levels. Most of them have fewer, but we can tell basically how many energy levels an element has by looking at its S energy sublevel over here. And so remember, these numbers down the far left side of our periodic table over here, if I'm in rows 1 through 7 as they're numbered on this side, then I have electrons in that many energy levels. So all the elements here in row 4, for example, have electrons in at least in their first 4 energy levels. And there's no electrons in their 5th, 6th, or 7th energy levels, which in fact then don't even really exist. Because if electrons aren't in those energy levels don't exist. They're not like empty containers waiting to be filled. They don't exist until there are electrons in them, those energy levels. At least in the ground state of atoms, when the electrons aren't excited then, they would be found in those energy levels represented by those numbers down the left-hand side. And so for any element on the periodic table, we can summarize its electrons, how many electrons it has, and the energy levels and shapes of what we call sublevels, the S, P, D, and F sublevels, found within each of those energy levels. So that's kind of the idea as we go with our work today into what we call electron arrangements. We looked at all these different sort of regions within the periodic table, from 1s to 2s to 2p, and so forth, all the way to the end of our periodic table, until we fill in all the different kind of sub-level regions up through all the way to the end here at 7p being our highest energy sub-level, the last ones to get electrons, and only in those last few sort of synthetic elements that we've made in labs would we find 7p electrons. So we don't typically work our way all that far up, but that is the idea as we work forward into our work with arranging electrons and understanding electron arrangements. And then finally, don't forget that the F block, as we think about it here, sort of exists within sort of that little gap between the S and D sublevels, and that it's sort of pulled out and stuck down at the bottom just for ease of sort of display and printing of our periodic table. So don't forget the F block is down there. We probably won't very often go as far as any of those elements that get past 6s, and only once you go past 6s does that mean you'll have to go down into that F block, which just isn't very common in the way that we work with these. Okay. So let's look at some examples. To do that, we have to sort of understand that all along we're going to be working with what we call the Aufbau Principle. The Aufbau Principle is a German term. It's not named after someone, but it's a term that means roughly building up. The idea is that electrons will always occupy the lowest energy position available, and we would say that the lowest energy position is the one that's closest to the nucleus. Lowest energy we're talking about here has to do with potential energy. And so that electron being furthest down, closest to the nucleus, sort of imagine it like if you picked an object up, if you picked it up off the ground just a short distance, just a few inches, it would have a rather small potential energy, which if you remember back from physical science has to do with height. But if I pick that object up a great distance, maybe many, many feet off the ground, it would now have a much larger potential energy because its height has increased so much. Its mass hasn't changed. The force or acceleration due to gravity hasn't changed. But that potential energy is great because its height is great. It's farthest from the ground, and so it has great potential energy. So electrons that are close to the nucleus, for somewhat the same reason, have a rather low potential energy in their position, their energy of position. And those electrons that are found in, say, levels 5 or 6 or 7 are significantly further from the nucleus on average, and so they have a greater potential energy. They're in a higher energy position. And we don't find electrons will fill those higher energy positions until the lower energy positions have been filled first. And at the bottom of this page here, you see the general order of things, and this order isn't something that you should have to feel like you need to write down or memorize. Because if you look back to what we've written on our periodic table as of last time, filling in those different numbers and letters, the 1s, the 2s, this is the exact same pattern that was on the periodic table that was on the screen just a moment ago. So if we go back to that, the same sequence, 1s, 2s, 2p, 3s, etc., 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 all the way down to the very last row, which ends in 7s, 5f, 6d, and 7p. That's what we have here. So those energy sublevels are in the same order as we see them there. And we have a few places along the line in here where you'll notice that there's, instead of less than signs, there's sort of roughly equal to signs. There are a few places where the sublevels are approximately equal in energy. And what that means is that the electrons have a little bit less consistency with how they fill those sublevels. 1s, 2s, those are all sublevels. They'll fill from lowest up to highest, with some of those places where the sublevels are so similar in energy. You see one here, here, we see one here, and then we see another region here. There's sort of four sneaky areas within the periodic table where the electrons sometimes seem to not necessarily follow what we would call a nice clean pattern. And it's because those sublevels are very similar in energy. We'll get to that as we get to that, but for now, don't worry about having to memorize the tricks or anything. There aren't really any tricks. We just need to understand that electrons do what they do, and we do our best to explain what they're doing in a way that we can make sense of and organize and make predictions about in terms of their behavior, what's coming next. So that lowest energy position will fill in first and build its way gradually up to potentially the highest energy position, or at least until you run out of electrons. Because in order to get to 7p, you have to have well over 100 electrons in the atom. And there aren't very many atoms that we're going to deal with that have anywhere near that many. Typically, we'll have somewhere far less than that. And we won't get as far as 7p. What I've got here is kind of a goofy upside-down version of the same periodic table, but I've taken it and flipped it on its head just to kind of help us think of the idea that 1s is at the bottom. And if we imagine filling this as sort of a funky-shaped bowl or a glass, or a pitcher or something, that all the water would go to the bottom and fill in those lowest points first, and then gradually it would fill its way up and up and up to the highest energy points. So you can almost imagine that the periodic table sort of makes a bit of sense flipped on its head in terms of where the electrons will fill first. They go to the lowest energy position first. And our lowest energy position, being 1s, is at the top of a traditional periodic table, but at the bottom if we flip it over. So just kind of another visual. If that confuses you, don't worry about it. If it doesn't, then you're set. Okay. Let's try some examples. Take a look at some examples here. And I'd like to work on some of the ones from your assignment. And if you go to your the assignment I'm talking about, that's this one, titled Electron Structure. And I believe, at least as far as we're working with it this year, it's on page 64. You might find it on a different page if you're not watching this video in the time that I'm recording it, which is in 2020. But you should have this page of practice regardless of when you're doing it with the class. And what I want to work through with you here are just some of the examples from this page. We're just going to have a few selected ones off of here. We're not going to try to work through certainly all of them together, but just a chance to kind of work through a few examples. And I'm going to work through with you magnesium right off the bat. Magnesium's the first one on here, and it's a good one to begin with. So on a periodic table, we have our magnesium there. And on a periodic table, magnesium has 12 electrons. Okay. Take a minute to find where magnesium is on your periodic table. And I'll pull my periodic table up here too. Okay, so I'm looking at the periodic table here, and if you're not real familiar with where all those elements are, that's okay. You don't have to be real fast. It's never going to be a race. But take a look and find those as we go. Let's get good practice just to find them. Here's magnesium. And remember, from stuff that we've been talking about earlier, we talked about magnesium, this blue number in the corner is the atomic number, right? Atomic number tells us the number of protons, but it also tells us for a neutral atom, the number of electrons in a neutral atom. So this is also the number of electrons. And that's what we're interested in for electron arrangements, is how many electrons does magnesium have? And magnesium has 12. That number right there tells us that a magnesium atom, when it's neutral, will have 12 protons and 12 electrons, so a neutral charge of 0. And so that 12 electrons is important because it means as we work with magnesium in our examples here, we need to make sure to account for all magnesium's 12 electrons. We want to be able to describe where those 12 electrons are in terms of energy levels and sublevels that we call S, P, D, and F. So magnesium, if we go to a periodic table and kind of understand how we laid those out on the earlier example there in the notes from the last video, magnesium with 12 electrons, you can kind of imagine, there's two ways to think about this, and I think you'll find that the other way is actually a little bit shorter for you, but I want to make sure that we're starting out with the basics, and then we'll work back to the way that you're probably going to use more often. With 12 electrons, those 12 electrons will fill in the lowest energy levels and sublevels first, and then gradually fill to higher and higher energy ones. And remember that sequence that we had up a moment ago, 1s, 2s, 2p, and so forth, going all the way up to 7p. Until you run out of electrons, you just follow that path. In our periodic table, like this blank one right here, which follows those notes from the last video, we could imagine filling in magnesium's 12 electrons then. We'd put an electron here. We put an electron here. Since 1s is the lowest energy position, this is where we always start. Lowest energy position with that, and that's Aufbau Principle, saying that the electrons will fill those lowest positions first. I've put 2 electrons into energy level 1, sublevel S, or shape S. So I would say that there are 2 electrons in the 1s, and we're not done yet, but I'm going to just write this down and work through this first one, very baby step. I put 2 electrons into 1s, and the way that we write that in chemistry is we write 1s2. This little 2 on the top here does not mean squared like it might mean in math. This little 2 on the top means a quantity of 2 electrons. So what this means to us so far, when I write 1s2, and you're going to write 1s2 for a lot of elements because most elements have more than 2 electrons, and they all have to start with 1s because that's the rule. 1s2, when we write that, it means I have 2 electrons, so the little 2 up there, that are in energy level 1. And we're going to bleed over here into rubidium space just a little bit. Okay, so that's what that 1 there means. And then the S means that they're moving in a spherical shape, or in a spherical region. Oops, moving in a sphere-shaped region, or spherical region. So that's 3 little pieces of information from that little code. 1s2 tells us that there are 2 electrons moving in a spherical region in energy level 1, or at that distance closest to the nucleus that we call energy level 1. Okay, so that's the first 2 electrons. Magnesium has 12 though. So what about the other 10? All right, let's go back over to our little guide here. And the next lowest energy position then is 2s. So I'm going to go ahead and I'm going to switch colors just to kind of make it different here. I thought I changed colors. Let's try it again. Okay, so we'll go with that blue. So that's 2 more electrons there because that's the next lowest energy position. Sorry, I went a little fast. That was in the 2s region, or the 2s part of my periodic table, which defines energy level 2 and those sphere-shaped regions again, the sphere-shaped path of the electrons. And so that's 2 electrons in 2s. I'll write it as 2s2. And again, that means the same sort of thing. 2 electrons. Now in energy level 2, moving in a spherical shape. Whenever I write S, it means that I'm describing electrons that are moving in a rather simple sphere-shaped region within the atom, or that's where they exist. Moving's a little bit simplistic, but that's sort of the term that we like to use. All right, so that's 2 electrons and 2 electrons. That takes care of 4. We still have 8 more. So where are the other 8? Back to my little guide. And by the way, I forgot to mention, this guide is on page 64. If you didn't already notice it there, it's on page, I think it's 64 in your binder, or else it's the previous page 63. It's kind of right there with this other assignment. And feel free to use these if you want to. You don't have to use them. You'll never have to fill them in, but they're sort of just little guides that might help you to sort of work your way through these as we get started with them if you're not real familiar with it. All right, so magnesium has 12 electrons, and we've only covered 4 of them so far. So we keep going. Well, what's next? The next region over here is the 2p, and I can put 6 electrons in that 2p section. And if I've got 12 to use, I've definitely got enough electrons to fill up all of that 2p region of my periodic table, which represents energy level 2, but electrons now that are moving in a cloverleaf-shaped path, all right? So I'm going to go back over here. That was 6 electrons in the 2p. So I would write it as 2p with a 6, and that means now that I have 6 electrons, right, in energy level 2, because that 2, that larger 2 there, is an energy level. The small 2's up above are a quantity of electrons. The larger 2's in front are the energy level that we're talking about. And then the P tells us that they're moving in or existing in, maybe we should try to use a little bit more official words, found in, figure 8 or hourglass, whichever of those descriptors you like, hourglass-shaped regions in level 2. So that's almost like a sentence. 2p6, which is just three little characters, right, represents 6 electrons found in hourglass-shaped regions in energy level 2. That's a really short way to write all that, right? Why would I want to write that big sentence when I can just write 2p6? But I have to know what it is, right? 2p6. Now that takes care of 2 and 6 electrons. That's 10. I'm almost done, but I've got 2 more. So where do those last 2 go in my periodic table? If I jump back over here to my periodic table, I've got 2 more to go. That row is finished. So the next thing I would do is I would go down here to this next third row, and I would block in those 2, and that would take care of it. And that would end all my electrons. So that's 12 X's that I've made now, so that's 12 electrons. And there are 3s, 2 of them in the 3s. So I've got 3s2. And again, that's 2 electrons found in sphere-shaped region in energy level 3 now. All right, so I won't write all that out again, but that's what that coding means. And so you don't need to write all these little descriptors and arrows and labels all around it. If I was going to write the finished final answer for this, right, I would simply write it as what we've got there in characters like, oops, I'm gonna get rid of my crude large pen here and get down to something tidy. 1s2, 2s2, 2p6, 3s2. That's the electron configuration. That's what we call this. 1s2, 2s2, 2p6, 3s2. This little code describes 4 very detailed sentences that we could write out, right? That we kind of wrote out here in our descriptions with those first examples. So we have 2 electrons in level 1. We have 8 electrons, right? These 2 and these 6 are both part, or all part of level 2. So that's 8 electrons in level 2, and then 2 electrons in level 3. That's another way to think about it. How many electrons are in each energy level, and then we can zoom in and be more specific and say that we have 2 electrons moving in level 1 as spheres. We have 2 electrons in level 2 moving in spheres. We have 6 electrons in level 2 found in figure 8 or hourglass-shaped regions. And then we have 2 electrons in level 3 found again in sphere-shaped regions. So that description is quite complete, and it tells us a lot about all 12 of magnesium's electrons with just a few characters that we write out real fast. Now, I mentioned that doing it this way by filling in the periodic table would seem sort of maybe unnecessarily complex once you get a hang of this. And what I meant by that was, if we take a look back again at the periodic table that we first found magnesium on here, I'll try to keep it all on the screen at once. All right, notice kind of where magnesium was, of course. Magnesium is right here on the periodic table. And if I think about where that is, well, of course, it corresponds right here to that section where we ended, right? This place where magnesium is found is the place where we ended on our little fill-in-the-blank sort of guide, template, whatever you want to call that little blank periodic table that we've been working from down there. And that's what I meant when I said in that last video. At any periodic table that we give you, you can go through and we can number the regions. We can number the rows. We can label the regions SPDF. We can identify those. And we should be able to make our lives pretty easy in terms of using any old periodic table to do the same sort of coding. 1s2, 2s2, 2p6, 3s2, and so forth for any element at all. So if you can figure out where on a periodic table the element is, and then take that spot where the element is and translate it to our little tool periodic table down here at the bottom, then you should pretty easily be able to work your way right to the end and just kind of like you know where to stop. Because knowing where the element is on the periodic table up here that you've got with your notebook, knowing where the element is sort of like knowing where the last electrons of that element will be found. The last electrons will be found there. and then you just have to fill in all the previous places with electrons and stop where the element is found. Okay, so let's work on one more example and kind of keep that in mind as we look at this example. I'm going to leave all my magnesium scribbles here. We're going to go to a fresh, clean periodic table, and I'm going to have you work on number 3 with titanium. Okay, if you wrote in a bunch of little descriptions and stuff up here on magnesium like I did, you might not have room for rubidium. You could go back and do it later on anyway. It's not going to be very hard. Once we get the hang of these, you should be able to just kind of knock them out and not really have to write any sentences at all. Now, where's titanium on our periodic table? Let's clear out my scribbles up here a bit. Titanium, right? Titanium is right in here. So I've got my titanium identified. And importantly, I know that it has 22 electrons. So 22 electrons for titanium, almost twice as many as magnesium. But keeping in mind then that titanium's 22 electrons and kind of where it is here in the periodic table, it's in that 3D section that we labeled in our earlier video and that we've been talking about a little bit today. It's in that 3D section, and it's in the second box of the 3D section. So kind of keeping that in mind, where titanium is, kind of remember that spot, and that translates onto this periodic table down below here. It translates to this spot right here. This would be the titanium spot on my periodic table, right? 3D, and it's in the second little box. So this one's scandium right next to it, and then titanium's right there. So if I know that titanium is in this little 3D box here, the 3D section of the periodic table, what I really need to do then is simply to get to titanium's 22 electrons here, I should be able to just start at the very beginning, as the line from The Sound of Music would say, start at the very beginning, a very good place to start. And I promise I won't sing it. But with 22 electrons, we're going to start at 1s and work our way up to ending on 3d. And specifically, we need to make sure we end in the right place with 3d. And we'll see when we get there what that means, okay? So let's work our way up with Aufbau. Remember, Aufbau means start with 1s and work until you run out of electrons? We can do that. Let's start with 1s. I'll try to keep that up on the screen here. Titanium's electrons. Sorry, my pen's a little jerky today. And every other day it seems like too. So titanium's, let's see here, 22 electrons. It's terribly scribbly. I don't like it when my pen isn't working real nice. I like to be neater than that if I can. So 22 electrons, we're going to start with 1s. And remember, 1s on for any element, 1s, it covers 2 of the electrons. So there's 2 of them. And then we run out of space there, and we have to keep going on to the next section. So just like in the last one, 1s gets 2 electrons, and then it's full. And then we go to level 2 of the periodic table, right? Energy level 2, 2s2, and 2p6. And again, follow along on your periodic table. You don't have to shade these boxes in or X these boxes in, but you're welcome to do it. I would fill all these positions with electrons for titanium. And again, don't think about those as other elements. Those are just electrons in titanium for our example right here in front of us. So titanium has 2 electrons in 1s, it has 2 in 2s, it has 6 in 2p, just like magnesium so far, right? What comes next? After that, we go to 3s, and we put 2 there. And we go to 3p, and we put 6 there. Now we've gone further than we did with magnesium, but we're going to keep going even a little bit further. So 3s has 2, and 3p has 6. So let's jot those down, just so we don't lose track of what we've done here. 3s gets 2, 3p gets 6. If I stop at any point, I should be able to add up those little superscripts and know exactly how many electrons I've accounted for or described in terms of their energy level and their shape of the region that they occupy within that energy level. So I can add up those superscripts, 2 plus 2 plus 6, that's 10, plus 2 plus 6, that's 18 total. So I've gotten 18 electrons accounted for. I still have to go with 4 more, right? And if I go back to my periodic table, that actually makes a lot of sense, okay? So I'll take one more look here. As I get down here to level 4, all right, let's see. Yeah, we'll go with that. For 4s, what the heck? I'm not going to use that thick pen. Pardon me. Did get my pens prepped. So 4s, we can put 2 electrons right there. And 4s gets 2. All s's get 2. Hopefully you've started to notice that when we fill up an s, 1s gets 2, 2s gets 2, 3s, 4s, they get 2. As long as I've got enough electrons to keep filling them up, it'll always be S2, 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 S2. Right, that's always the case. And that sort of was in the last video as well. Now that only gets us 20 electrons if we add up those superscripts. So what about the last two? And that's where we get right in here to 3D. And so to wrap up with 3D, and I'm just going to erase this for now just so I've kind of got my spaces back. We know where we're headed here. 3D, to fill up to that last point where titanium is, we'd need to put 2 electrons in there. Now look, we talked about in the last video, right? 3D, as with all the Ds, has a maximum space potentially of 10 electrons, but it doesn't mean it has to have 10 electrons. That means that's the maximum, right? Just because it's got room for 10 doesn't mean it'll have 10 in it at all times. So titanium starts putting some electrons into level 3 in those cloverleaf shaped regions, but it doesn't have enough electrons to fill them all. It does not have enough electrons to fill them all, and so it only fills a part of it. It's partially filled. This we would say that that's a partially filled sublevel 3D. It's holding 2 of its potentially 10 electrons, and that's okay. We put 2 in there. That's what we need to write down in our notes. So as much as it's got a room for 10, it's only got 2 in it right now. So 3D, let's go back up here. 3D has 2 electrons in it, and that's the end of my sequence. Now, I think just to kind of make my color pattern more, oops, what the heck? I think to make my color a little bit more consistent, I'm going to make that green to go with level 3. And so I've got here 2 plus 2 plus 6, that's 10, plus 2 makes 12, plus 6 is 18, 2 more is 20, and then 2 more is 22. So that's all 22 of my electrons, and that would be titanium's electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Okay. Now you might say, whoa, Bleth, wait a second now. That's a lot. I had to take a breath like twice in that. That was so much to say. Okay, well, that's okay. You don't have to do it in one breath. But you might also look at it and say, hey, wait a second now. How come we started level 4, we went to level 4s, and then we hadn't even finished with 3D yet? How come you went to 4 before you finished 3? It feels like you're jumping around now. And it is going to feel that way a bit. Here's what we're looking at. Remember back on this slide, the last time things that we looked at in the slides from just a few minutes ago, that there are places along here where the energies are very similar. And 4s and 3d are one of those places where 4s and 3d are basically equivalent in energy. And that means that electrons don't necessarily seem to fill in what we would call a predictable way. You might say, well, 3d should come before 4s. We should do 3d and then go on to level 4. Because they're more or less interchangeable in energy, we might find sometimes that electrons seem to behave in a way that agrees with you on that, and other times maybe not so much. So in this case, 4s is just so slightly, we might consider it here, so very slightly different from 3d that it'll fill up first. And we might find that in a different case that it seems to go backwards and 3d might get electrons first, or it might make more sense for 3d to have electrons and 4s doesn't have any. Those are all very specific little nuances and details that honestly we don't fully understand yet in chemistry. And so you're not going to have to explain why 4s comes first before 3d. All we need to know is that there are some sweet spots in there, and you can assume at all times that if there are electrons filling into 4s ahead of 3d, like we see with like our situation here, 4s seemed to fill first, that it's not necessarily that level 4 is lower energy than level 3. It's just that parts of level 4 overlap in energy with parts of level 3. The lowest part of level 4 is very close, or even maybe similar enough to be called equal to the very highest parts of level 3 in terms of energy, and they overlap. It's not quite like boxes stacked on top of each other. It's more like sort of clouds that sort of overlap slightly with each other. And so those energy levels sort of seem to overlap a little bit too, and it's going to feel like we're kind of going a little bit out of order. We're not, I promise, but it seemed a little bit funny at first when we start working with questions like that. Keep that. I'll go back over here to finish up our example here. So that was titanium, and again, I would just put all that in one color when I was writing it down, but kind of get the sense of what we're doing with that one here. Okay, so let's do one more. We're going to just kind of work with one more here, and that's number 7 in selenium. I'm going to work with that one for you yet. Selenium on our periodic table, go back to our main periodic table here. Selenium is way over here at element 34. Okay, so here's selenium way over here on the right side of my periodic table. And kind of thinking about where that is, right? We know we were just talking about 3D with titanium, so it's in that section that comes after 3D over here. in the right side of the periodic table, and that's that 4p section. So selenium is in that 4p section, and it's in the 1, 2, 3, 4th spot in the 4p section. So if I think about selenium here in the 4p, and I'm going to go down here to one more clean one. Okay, selenium would be right about here with its 34 electrons. And we need to account for all 34. Now, like I said, this is going to feel a little bit sort of familiar because we're going to start with 1s every time, and we're going to work our way up and up and up and up and keep going until we run out of electrons. And in this case, we have 34 electrons to take care of instead of what we had in the last one, which was, what, 22. So we had quite a few less. So to get to 34 electrons, to get to selenium, again, we're going to start with 1s because that's where we always begin. The 34 electrons for selenium. And if you kind of think about knowing that it ends at 4p, that's like knowing sort of where the cup is on a golf course hole or a mini golf course hole. Like where am I trying to end up here by the end? That's not where I'm necessarily going to get in my first stroke on the golf course, unless I'm really good. But maybe that's where I know I'm going to try to get there by my 3rd or 4th stroke, or if you're not much of a golfer, your 10th or 11th stroke perhaps. But you get there eventually, and knowing where you're going is half the battle. Well, maybe not half, but it's part of the battle, because you do need to get eventually, right, to where you're headed, and that's to that selenium position at the 34th electron. So selenium's electrons will follow the same Aufbau path we've been writing up all along. 1s2, 2s2, 2p6, and we'll go over to the picture here in just a minute and make sure we haven't done anything wrong. 3s2, 3p6, okay? Now if I add up my total at that point, that's the first 18 electrons, right? So 1s2, 2s2, 2p6, 3s2, and 3p6 would get me on my periodic table here as far as, and I've used red all the way, so I'll just red those in. I've gone as far as 2p6, so that gets me to here. We need to go a bit further, right? Oh, sorry, we've gone as far as 3p6, so I'm going to go even a bit further now. Gets me all the way out to here. And again, do not feel like you need to check in those little boxes. If you're getting comfortable with this, you just do it. You can slide your finger around on your regular periodic table and just know where you're stopping. Sort of have that as your flag on the golf course, and then just quit when you get there. All right, so the next line will be 4s, and I'm going to switch over to blue because we're switching to a new line. 4s2. And then that 3D, and we're going to go all the way through 3D because we're going beyond it. So I'm going to fill 3D all the way to its 10th position. So that's 4s2 and 3d10. Let's jot that down, and then we'll put the finishing touches on selenium. 4s2, 3d10, and then we end on 4p, we said, right? That's the selenium is found in the 4p part of the periodic table, we would say. And that just means that selenium's last or highest energy electrons are in the 4p position. And we'll describe again what that means for selenium. But that's 1, 2, 3, and we do count the box that it's in. That's 4. So to fill up through that box and no further would take 4 electrons in the 4p section. And so let's go over here and put that in. Then we'll put a little summary here at the end of our description. So 4p4 for selenium. And that again, if I go through, if we can do some quick math, 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is another 10. And then here's another 10. That's 30 up through 3d10 plus the 4 more at the end. So that is 34 electrons if you add those up. And you can certainly use a calculator to double check yourself, on any and all of these as you're going. But by all means. What does that last little part mean? Just to kind of put a little bit of a detail on that, these last electrons we could describe then as selenium's highest energy electrons. And a short way to say that, we'll often hear ourselves describing them as the last electrons. The last electrons in selenium, are found in figure 8. Let's try that again. Found in figure 8 or hourglass shaped regions. So we could define that about those last electrons. At a distance that we call energy level 4. Now, that's again all human design, right? This is all what humans are saying. they're in level 4. They're at a greater distance than level 3 electrons, and they're not quite as far as level 4 electrons, or level 5 electrons, rather. All this is human stuff, right? This is all human construct we've put to electrons. They don't know that we're calling them 4p4 electrons. It's just our best attempt as humans to describe what we've seen and observed and things that we maybe don't understand fully. And it's our way of explaining it to others and passing that information along to each other. It's a way of communicating information. And that's vitally important to understand and to look for patterns in chemistry. Understanding chemistry is largely understanding patterns. And if you can't look at a periodic table and elements and sort of start making those connections, you're going to have trouble with some things we'll do later. So it's understanding then that 4p4 means that selenium is going to have some things in common with other elements that have something similar at their endings as well. And those endings are really important. Selenium's got a lot of electrons in hourglass-shaped orbitals. These 2p electrons, those are in hourglass-shaped orbitals. They're just closer to the nucleus, so we say they're in level 2. These 3p6 electrons, those are in hourglass-shaped orbitals, or regions, and they're just a little closer to the nucleus than 4, but not as close as level 2. Right? And then these last ones at the end, those 4 are in hourglass-shaped regions again. And so 2p6, 3p6, 4p4, those are all electrons found in hourglass or figure 8 shaped regions. And so if I was to add all that up, 6 and 6 and 4, that's 16 electrons that are moving in some kind of what we would define as an hourglass shaped region or a figure 8. The other one we hear sometimes is a dumbbell shaped. If you imagine the dumbbells with the weights on the two ends. Me, not much of a weightlifter. I can't relate as much to that, but I do know what a dumbbell is. So it does make some sense. So the rest of these on here, I'd like you to try for yourself. Keeping in mind here now that there's a little section on the far right edge of this page that we've kind of blocked out here for what's called a Lewis dot diagram. You don't need to worry about those yet. You might have done those before, but we'll catch those in a later video. So just leave that space sort of clean, and we'll work with Lewis dot diagrams later. But try to do the rest of these elements. If you can do all the rest of these, you're doing great. The 13th one on there, dysprosium, is a little bit of a beast. So if you don't feel real good about dysprosium, that's okay. It's probably beyond the needs of our work. But give the rest of them a try and see what you come up with. Okay? And we'll check the key and we'll take it from there. Until I talk to you again, thanks for listening and good luck.